wasn't, make sure you check in with me, because for most of you we already had a plan, but for some of you we don't. I think the people we didn't have a plan for are not here, so definitely. Okay, we are going to begin on lesson 7 today, which I think is page 21. Is that right? Page 21. Based on what's happened first and second period, I need to adjust your homework this evening, because what has been evident is that 1 through 3 is actually too much for you to do today. So you're going to omit number 2, which means you need to only do 1 and 3, not 1 through 3 this evening. And we're going to model how to do those today. You'll turn them in tomorrow, get feedback, and then we'll continue building this skill tomorrow. I'm going to warn you. The algebra that we're going to be going through is a little bit scary. And it's also just unfortunate that this lesson is happening on a Monday that you're in PJs, no less, which makes you just a little bit more like than normal. So that's okay. But we will survive it. As you guys find your way to page 21 and I get my computer plugged in, because I'm going to start with a computer demonstration. If anybody has corrections from that limit ad infinity assignment from last week, or if you were not here and you need me to have that, let's also deal with that in the next 30 seconds as well. Anybody other than Giselle? Oh, Vanessa. Okay, perfect. Thank you, you two. And let me get my computer plugged in. Okay, so I'm going to start today with a demo on my computer to help kind of ground us in where this conversation is heading. I'm going to ask one of you to click for me so that I can be freed up. Don't look at any of this. There we go. What? Oh, what a booger. What a booger. I'm going to ask someone to click. Maybe Brian, because you're right there at the head of the class. I'll keep you awake because everybody's so sleepy. But before we start clicking away here, I want to ground you in the conversation about where this is going. Because the last week and a half or so, we have been really focusing on limits, right? Graphical limits, numerical limits, algebraic limits. We've done a whole bunch of limit computation over the last several days. And today we're really shifting gears to begin a discussion on derivatives. Derivatives are something some of you have heard about, like you've heard me talk about these, maybe you've seen some calculus posters on the walls involving derivatives, and today is the day that we finally get you a little bit of exposure into where this can really head. Derivatives are really, really closely aligned to slopes, which are something you've been studying since algebra, right? Help me out, how do you find slopes? Rise over run, that's one I hear. Just brain dump, as many ways to find slope as you can. There's one I hear from Abrielle. So rise over run could also be expressed as y2 minus y1 over x2 minus x1. What else? That's the equation of a line, which would use the slopes, yes. But there are a couple other ways I've seen people come up with slopes. No? Have you seen that one before? Change in y over change in x, maybe? Maybe more of a physics approach, I don't know. And the other one I was telling students is, like, if you're feeling fancy, you could also write f of b minus f of a over b minus a. This is like average rate of change slope, but still a couple of y's and a couple of x's in the bottom. And in these conversations that you've had in the past about slope, in order to actually get an answer, how many points did you always have to have?
3. 4. 2.
2 points have always been necessary to compute slopes, right? Like especially in this one, y2 minus y1, you see really clearly, oh, I've got to have 2 points in order to be able to use that formula. And that's been true every day of your math lives until today. So I'm super excited because this big idea of a derivative actually allows us to find slopes of lines given just 1 point instead of 2 points. And that's kind of like, if you really think about it, you might be thinking, well, how in the world is that possible? How can I use any of those formulas only given 1 point? So that's what this demo is going to help us out with, and then we're going to actually formulate a new idea, a big formula that we'll be using throughout the remainder of this unit. And definitely also picking up with next year if you find your way into a calculus course. Okay, so you see your function, right? Nice, beautiful curve right here, and a single point on it. What we're going to try to do is find the slope of the line that would be connecting point P with this curve right here. It's called a tangent line that we're going to visualize in a second when Brian does something for us in a minute. First things first, tangent line is one kind of line we're going to be looking at, and a secant line is another kind of a line. A secant line, if I scribble on this, would have to intersect the curve twice. That's always the definition of a secant line. Goes through 2 points on your curve. And that's like old school, right? If I had 2 points on the curve, could I find the slope of that yucky red line I just drew? Sure, using any of the formulas I just erased. The more interesting conversation, though, is the slope of the tangent line. Tangent line touches your curve once at what we call a point of tangency. Here, P is the point of tangency. And our big goal is going to be to find the slope of that red line, which would appear to be a little bit more difficult because I only have 1 point instead of 2. So there's going to be our motivation for really trying to get our heads wrapped around what it is that we're talking about here. Brian, do me a favor. Can you click on number 1, that gray box tangent segment at point P, while I give Carla his question? Okay. Keep track of your own time. You cannot use your calculator until you get to question the middle. You only have a calculator. You can take it like this. Get your phone out. Keep track of your time. Okay, so can you agree based on what I just said that that's a tangent line? Only intersecting the curve in one place at P. And when he turned that on, that number Abrielle shouted out earlier popped up on the board, right? The slope of that line is 2.819. And what we really want to try and figure out is how in the world the computer is getting that number, because we couldn't do it yet by hand with any of the formulas that we have at our disposal. Okay, click arbitrary point, and everybody look down here on the x-axis as he does that. Okay, so what the computer program is going to do for us is take this arbitrary distance h and create a new point h units away from x on the x-axis. Number 3, Brian, create q. From that value on the x-axis, then, we're going up, 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 up to our curve and creating q. You okay so far? Maybe. What? We don't need him yet. We might need him in a little while. I heard Jesus. Okay. Number 4, secant PQ. Secant line, yes? Yeah. Because it intersects the curve twice versus once, our tangent line. The slope currently of PQ is 4.285, which, let's be real, is nowhere near 2.819. And I think you can see that visually too. That green line clearly doesn't have the same slope as the black line quite yet. If it did, they would be running parallel to one another. So what we're going to do here is attempt to create a mechanism for allowing that secant line to begin to mirror the tangent line. And the computer animation is going to help us out. Before we do that, Brian, do me a favor, scroll over. I want everybody to see the coordinates of Q, and for some reason I haven't figured out how to zoom on this thing, so thank you. Right now, as is, we've got a point at P, we've got a point at Q. So with algebraic strategies, I know exactly how the computer is finding the number 4.285. Simply taking a slope formula of y2, by the way, here's x1, y1, x2, y2. So they're just saying, well, I've got a y2, let me subtract y1 and divide by x2 minus x1. That's what the computer is doing behind the scenes to get 4.285. What we're unclear of right now is what it's doing behind the scenes to get 2.819. But Brian's going to click one button for us, and I think it's going to uncover where that top number is coming from. But are you ready? Because you have to watch it kind of runs through. We need to make sure we're paying attention. And it's annoying. Scroll back and then hold on. Hold on. Jeanette. What? I don't know. It's right here, across the street. You want to see it though real quick right before you go? I know you're so intrigued. Okay. Yeah, never mind. Whoa, okay. So here's the really big idea behind calculus. What we're going to do is take two distinct points. Notice P is not moving, that is stationary. But Q, the arbitrary point, is moving closer and closer and closer to P. And as that happens, check out the slopes up here of the secant line. I hope you can intuitively see here that right before it resets, it's getting really close to 2.819, right? And I think, and we're going to have Brian test it out in a second, the closer Q gets to P, the closer that number is to the actual slope of the tangent line. Okay, so you're going to get put to the test. Diego has set the bar very high during first period, and he froze this almost in exactly the right spot. Who was it second? Who was my mouse? I forgot. Who was my mouse? Harold. Oh, Harold did not do as well as Diego. He did not. Okay, so to freeze it, you're going to unclick right there. And Brian, you want to try and unclick in just the perfect place, okay?
I need to do.
Okay, that's fine. You go when you're ready. That's fine. You're trying to cheat. What a booger.
Dude.
Oh!
That's good
There. That's pretty good. That's pretty good. You want to know if you were better than Diego? No. He got like freakishly close. Like the first time, I was like, that's never happened. Never. He did really good. Okay, but you can see, and I'm especially glad that there's color coding here because I think we can agree Q is not right on P, right? There's still some overlapping right there. So even with our finite ability, I could find the slope using an old mechanism right there because they're not the same point. Two distinct points, I would do y2 minus y1 over x2 minus x1, and it looks like I would get 2.851 when I ran through that formula, which is close to 2.819. So one of the big ideas here, if I want to try and move from needing 2 points for slope to just needing 1 point for slope, that second point needs to get as close to the first point as possible, right? And essentially, if I could get them to be right on top of one another, how many points would I really be looking at? Just one instead of just two, if they're identical, right? If they land right in the same spot. Try one more time. Well, actually, just run it for me on a loop before you freeze it. And I want to draw your attention to H, because you've been looking at the points, you haven't maybe necessarily been focusing on H. H, remember, is that distance between Q and P on the x-axis. So as Q gets closer and closer and closer to P, what's happening to H? Decreasing, for sure. What's H getting close to? 0. Yeah, absolutely. H is approaching 0 as Q approaches P. That's cool. This, can you also agree, has Q going in from the right-hand side? I hope you can kind of see some similarities to our conversations about limits here, especially with some of the words that I'm using, like approaching P, approaching 0 from the right-hand side. We should technically also be approaching from the left. So the middle button there, go ahead and turn that one on, Brian. Show from left as this one's running. Okay, so there we go. We've got another point now on the other side. It's a busy graph, yes. But you've got slopes now here as well, and we'll put Brian to the test again in a minute. But I think you can see as they both converge to that point P, from either side we're getting closer to 2.819. And we want to see if Brian can try one more time, right? And see how good he does here. Whoa! Woo! That was pretty good. That was really good. And I was looking down here. They're like all right on top of each other, right? And take a look at these. 2.807, 2.832, 2.819 is right in the middle, right there. So what we're going to talk about is how we, without the aid of the computer, can get values like that for these slopes of our tangent lines today. Did I already tell you we're omitting number 2?
Yeah.
Okay, cool. So we're going to focus our energy today on quadratic functions because 1 and 3 on your homework are mirroring quadratic stuff, and I want to get you comfortable with the algebra necessary for handling those situations. Tomorrow we'll deal with like fractions, rational functions, and maybe some trig, things like that. Okay, but right now we're going to keep it at a little bit nicer of a level. So thank you, Brian, for doing that for us. You did quite well. I didn't anticipate the double clicking, though. That was a nice thing I hadn't seen this morning. So let's go to 21 and kind of answer some guiding questions here before I review the formulas for you. Okay. So in this box under Explore, we're told that up until now, whenever we've discussed slopes of a curve, we've had to consider 2 different points and then use those points to help us find our slope. Today is a good day because we're able to expand our knowledge and develop a way to find the slope using just 1 point. I even wrote, way cool, so that when you go back you can realize, like, super cool. Judging by the looks on your faces, you are just so excited about learning this right now. Number 1. Okay, in order to answer number 1, I need to remind you. The point P was at x f of x. The point Q was at x plus h f of x plus h. Do me a favor, using y2 minus y1 over x2 minus x1, please find the slope in a very general sense between those 2 points. I did it a second ago, just see if you can remember. Take about 1 minute with your tables, get me the first slope. Alright, so here's what I'm expecting to see. Your y2 minus y1 over your x2 minus x1, right? So I had a second ago. Can anybody recognize any simplification that can occur to that formula that we just created? What is me? Where? Which one?
X plus h.
Ah, close. But unfortunately, because there are minuses, that's out. But there is somewhere I can. X and x in the denominator. So positive x and the negative x down here. So if you're wanting to simplify, a cleaned up version would be f of x plus h minus f of x over h. All right. Now, from there then, here's where we're going to try and develop this strategy. Ultimately, what we are interested in is finding the slope of the tangent line at just P. So visualize again what was happening on that demo. P was stationary, Q was up top. And when Brian clicked, where did Q start to head? Down towards P, right? So the big idea here behind transitioning from needing 2 points to 1 point is that that secondary point needs to approach our initial point, our stationary point. So how can we do this? We are going to let Q approach P. And notice that's very, very like limit language right there with the word approach in that statement. Now, as Q moved down toward P, what was happening to the numbers that were scrolling through at the top of the screen? That first number was always 2.819, right? But as Q moved down and the secant line started shifting, what was happening to the second slope? Got closer to the first one, right? So let's see. what happens to the slope of the secant line when we move P closer to Q, or another way, what happens as that H gets smaller and smaller and smaller. I was seeing that the slope of the secant line approached the slope of the tangent line. And in a perfect world, like we all live in a perfect world, we've got capabilities that sometimes don't do exactly what we want. Like we were limited by the quickness that Brian could click on the mouse, right? And even though he got us close, was he able to get us exactly there a second ago?
Yes.
No, those numbers weren't the same. They were very close, but they weren't quite there. In a perfect world, though, I think we maybe would hope to see that that value of H actually went to 0. And we saw 3 numbers at the top that were identical, identical, identical. Right? Man, we're getting all kinds of... Yeah, thank you. You're welcome. Okay. So what would happen when H equals 0? That's best case, right? If I could find a way for H to equal 0, my slopes would be the same. And that's kind of what I'm hoping we can figure out a way to do, but we're going to run into some trouble. Let's see, what would happen when H equals 0? I'm going to be very vague here, even though this says be specific. I'd have equal slopes for the tangent line and the secant line. The trouble, though, with that, and the reason, like, Brian couldn't actually click his way to equal values, notice up here, if that were possible, and he could have found a way to get H to be equal to 0, what would happen in this formula right here if we let H be 0? Something bad in the bottom, for sure, right? Dividing by 0 right here. Up top, what happens if H is 0? F of x minus f of x? 0 over 0, you mean, is what's going to come?
No.
Oh, no.
No.
Right? So although I want H to be 0, because if H is 0, that means Q is like landing right on P. Even though that's what I want in my best case scenario, that's not a good thing for the formula, because I'd be getting 0 over 0. But the great news is, and this question says, is there a way we can find the slope of the tangent line every time without having to keep making H smaller and smaller and smaller? What notation provides us with that ability? It's limit notation that allows us to do this. And I'm going to introduce our formula right now. The first one, you'll see some huge alignment to the answer on number 1. And then I'll give you a second formula because most students like that one better. Let me erase this real quick. Okay, definition of derivatives using limits. Check this out. We just saw that the slope of that secant line was f of x plus h minus f of x in simplified form divided by h. What we're trying to find now, and here's new notation, is the slope of the tangent line. M for slope, a little tan at the bottom to represent tangent line. And I can find that slope of the tangent line by just making a minor adjustment to the slope of the secant line. And instead of just looking at this finite y2 minus y1 over x2 minus x1, I'm going to add a limit up front. And I sure would love for h to approach what number? 0. Exactly. And I think you're on board with that because you saw what was happening to that finite distance of h getting smaller and smaller and smaller as Brian clicked. And I think you can agree, I don't want h to be 0. Because when h is equal to 0, oh no, I'm in a really bad situation. But limits don't care what happens at 0, just what happens as we approach. That is why this is such a powerful, powerful idea. This formula bliss is pretty trying in terms of the algebra that we're going to get into. So I definitely want to introduce you to a second alternative that in your homework it says using any option. So I'm going to model both and you can use whichever one you want. The second formula is still a limit. But this one has no h's in it. Students tend to be very confused by the h's that are showing up in that first rule. This one is as x approaches c, and I'll tell you where the c comes from in a minute, of f of x minus f of c over x minus c. I'm purposely going to model the harder one first before I show you the one that students tend to think is a little bit easier. But there's a lot of value to using this one that I'll also try and justify in a few minutes. Okay, let's try our first example on page 22. First thing you need to know is that at the top of the page are just the same formulas that we recorded on page 21. So I'm not going to spend a ton of time there. I'm going to get to the model problems. First model problem, example 1. Find the slope of the line tangent to the graph of y equals x squared at 1, 1. So our first method, slope of the line tangent, by the way, that means m tan. And I just came up with 2 different formulas I could use to find m tan. Method 1, I'm going to use formula 1. That's the limit as h approaches 0 of f of x plus h minus f of x over h. And what I need to try and figure out here is how to substitute into that formula for this specific function that we have been provided with on our first example. I'm going to walk you back to a conversation maybe you had in Algebra 1, when you first took Algebra 1, before I dive into this. Because I'm going to share with you some common mistakes that students make. And you'll be like, I would never do that. And then sometime in the future, you might do this on accident. It's very easy to fall for some of these tricks. First of all, can we agree that in this case, our function, for example 1, is x squared? That's the curve that's been given to us here. Sorry, it's messy. So what I'm really trying to figure out is like what to replace f of x plus h with and what to replace f of x with. Not a lot of doubt in my mind what to replace f of x with, because I know f of x is x squared. But students make a lot of weird decisions about that first term. Back in algebra though, you were little, remember, you were not as comfortable with some of this stuff as you are now. And this may have been a rigorous problem for you back then. I know. I know. You know the answer is 9, right? Back then, you may not have been able to jump right to 9. So what did you have to do to get your answer? Plug in. And your teacher was probably very strict with you about you plugging in with parentheses, putting a square up top, dropping a 3 in, right? And then you do the math, you get 9. They may have made it more rigorous after that and said, what's f of 51 or something like that? Scary. And you were like, oh, I don't know, but I know my steps are to open the parentheses, put a square on the outside, and drop 1 inside. 51. And maybe you would sit for a minute and do the math. When they really wanted to confuse you, they would say f of, I don't know, like a negative with a fraction maybe. And you were little and you were like, I can't do that. But you could, especially if you had this structure. You would open your parentheses with your square and drop in a negative 3/4. Then there came the day when you discovered math was not all numbers and there were letters involved too. And your teacher may have said, what's f of m then in this scenario? And you were like, in your, young way, what do you mean f of m? And you, at least you had a structure in place and you dropped an m in that square. Thank you. Okay, you with me? Here's what I'm asking you to do in the context of this formula. I don't need f of 3 or f of 51 or f of negative 3/4 or f of m. I need f of x plus h.
What?
And even if I'm a little bit concerned right away, at least I've got 4 different examples here of the right structure to use to approach this particular question with. I would open a parentheses, top it off with a square, and what am I going to put in these parentheses?
1, 5, 7, 51.
I know you think you're being funny, but that's how people get confused, so stop. Someone will hear you half asleep and be like, oh, 1,051, that's the answer.
That's where they went wrong, they shouldn't be half a step.
True. And we could go back and forth about that for a while, that's true. But let's try and approach this with this same idea. When it was f of 3, 3 squared. F of 51, 51 squared. You get it, right? F of x plus h means x plus h squared. And I think with this setup, you're like, how could anybody make a mistake on that when this crazy lady showed me it in painful detail 5 times? Can I show you what students do all the time? They know their function is x squared. They see f of x plus h, and they write x squared plus h in their unit, which is not the same as what I have right here. This, if you want to know in function notation what you just found, is the function plus h afterwards, right? What we need is the function evaluated at x plus h. That means the x needs to go out and the entire sum needs to go in. And this is something that students will do incorrectly over and over and over again. So when in doubt, go walk yourself through some simpler processes to help you out so that it seems less weird when you go in with the x plus h. And that's just the very first step of this intense process. So I want to make sure I emphasize that you have to be careful to do that part right. You make a mistake there, you're in trouble for the rest of it. So I'm going to replace. I've got a limit as h approaches 0 up. What we just decided is the function at x plus h is x plus h squared. Minus. What function are we looking at here? What did they ask us for? Slope of the line tangent to the graph of y equals x squared. My function is an x squared, and I'm dividing by h. I know a lot of you are very visual, so let me try and show you what this question is actually getting at. The graph of x squared is a concave up parabola like this, and there's a point on that curve at 1, 1. What we are trying to uncover right now is if I were to draw a tangent line at that curve, what the slope of that black line would be. That's our goal. I hope you can look at that and realize it's going to have to be a positive number because the slope is increasing, and the line is increasing. But what that number is what we're going to try and get to the bottom of. With limits last week, if I didn't have a graph, I didn't have a calculator, my first option was direct substitution, right? And hopefully you can see if I attempted direct sub right here, I would get 0 in the bottom for sure when I go in with a 0 for h. And up top, if I take the h out and put a 0 in, I actually get x squared minus x squared. A 0 up there as well. So I got to do some work here to get to my answer. And I'm going to show you the next thing that students do wrong in this scenario, which actually makes me more mad than the first one. I get the first one. The h is confusing. But this is something we've been harping on for years. How do you square x plus h? Thank you. It is not in any way this arrow thing that calculus students love to do. Distributing a square has never been a legal move. To multiply something by itself, we've typically used a box, right? Because that means x plus h times x plus h. That's x squared. Let's see, what's my next box going to have in it? xh or hx, depending on which way you want to write that. Another matching xh followed by an h squared. So when I think about how to manipulate my fraction over there that's getting to be a mess and try and simplify my life, here's one way I could simplify it algebraically. That makes sense. Sound algebra. The x plus h squared right here actually results in an x squared plus 2xh plus h squared. I still have the minus x squared from up there and the over h. And luckily from here, if I look very carefully at my numerator, I notice that a couple of terms eliminate themselves up top. You gotta look carefully, but I've got a positive x squared leading my group and a negative x squared at the back. So those can definitely be canceled. And I'm left with a limit as h approaches 0 of 2xh plus h squared over. I'll give you a second to record. Very easy to want to cancel here too. I purposely wrote the h's right on top of each other too to make you think you might want to cancel. But that's a plus right now. It can only cancel through multiplication, not through addition or subtraction. Algebraically speaking, anybody have ideas here? Because I believe some of you probably know what algebra to do next before I have to see. Yeah.
Could you take off one of the squares? Like put h times h and then cancel two.
Okay, so you're thinking right here, there's actually, if the h is squared, an h times an h, right?
Yeah.
Now, I like that mindset. However, canceling this way, I'm not ready to do yet, because there's still a sum going on. But, hold on. I think that when we write that h squared like this, we can see a little bit clearer that there's a common term in both of those pieces up top. Just in my numerator, I've got an h over here and a common h on the second term. So how about I factor out the red one and write what's left over? Because then I'm transferring this into a multiplication problem and I could get rid of the h's. But writing it like that helps us to realize what would be left, I think. So let's see. Limit as h approaches 0 of. I'm going to get rid of the red h. On the first term, what's left if I take out the red h? 2x. And up here, if I take out the red h, I'm left with another h, right? Oops. And I've got the red one down low as well. And now that those terms are multiplied, they're gone. And by the way, from a limit perspective, as soon as I canceled those, there went the 0 over 0. Goodbye. I just fixed the problem that I was running into earlier. Once that problem's gone, we do direct substitution for whatever this value is approaching on the outside. H is 0, right? H is approaching 0, so this becomes 2x plus 0, where the h was, for an answer of 2x. Now, a lot of students don't like this approach because they come back to what they were trying to figure out and they're like, what? That makes no sense. I was supposed to be determining the slope of that line. And the slope of that line can't be 2x. It's got to be a number, okay? And so we have to do one final move right now. It's not a lot, but it's something that pushes your critical thinking a little bit. What we just decided, and I'm going to introduce you to some kind of intense notation right now, is that the slope of the tangent line at, notice I just said at when I drew that vertical bar, at any point xy, points always come as an x and a y, is equal to the formula 2x. That's what I just determined. I can find the slope at any point using this rule right here. Our problem doesn't want the slope at any xy, it wants the slope at 1, 1, very specifically. So I'm going to communicate that I would like the slope of the tangent line at 1, 1. Which means I've made my x a 1, right? And my y a 1. So could I perhaps evaluate this at my point? 2 times 1 for an answer of 2. And I think you can probably agree that the slope of that line, it makes perfect sense, could be equal to 2. The reason I love this strategy versus the one we're about to do in a second, if I can dig through all the math, I have now done one limit problem. Was it intense? Sure. But I did one limit, and I can now find the slope anywhere I want. Because if you've previewed your homework, I give you one function, but I ask for the slope in a couple of places. So now if I wanted to do the second part, I could just plug into 2x and get no answer. The downside to the second strategy is that if I want to ask you about the slope at a variety of points, that means you're going to have to do the limit over and over and over again and start over every single time, which I don't think you'll be a huge fan of. But I'll give you that option. So we'll try method 2 real quick and see where we're at with time after this one. Method 2 is the formula with the c's in it, so I'll start just by writing that down. M tan equals, the limit as x approaches c of f of x minus f of c over x minus c. We're going to try this one more time with a different strategy in case you want this one, or you like this one more. The biggest question here is if I want to use this formula, what is c? Because without knowing c, I have a hard time substituting. So the good news is, that point that I give you, the x value is always your value of c. So knowing that, I can substitute in everywhere I see a c down here and replace that with a 1. That's what I'm going to do first. This problem's actually asking me for the limit as x approaches 1 of my function minus f of 1 over x minus 1. The c's came out and 1's went. If I attempted direct substitution right away, 0 over 0 would be the result. So I'm gonna have to do more work every single time. Remind me, what function is it that I'm dealing with right now? X squared. How about I replace the function with the actual equation x squared? Start to visualize what's going on with this limit. I could actually substitute in for f of 1 as well, based on the information that's been given to me. This is asking us, what is the function output when the input is 1? It's 1. You can look right here at the point if you want, or you could plug a 1 into x squared and you get 1 out either way. But the good news is, f of 1, I know what that is. It's 1. I should say, please be careful, they're not always going to match. That just worked out on this example, that when I substitute a 1 in, I get a 1 out. Okay, if I tried direct sub here, 1 squared minus 1, 0. 1 minus 1, 0. I'm still getting, oh no. But I feel like this is a scenario I'm more comfortable with that I could definitely simplify. A squared minus b squared up top, right? That's one of my favorite factoring rules. You guys remember how you can break that apart into 2 groups up top, Gabriel?
Plus 1 and x minus 1.
Perfect. Let's not forget my limit. That's so helpful because now the x minus 1s are gone. And if you're remembering, that's where the 0 over 0 was. So it's great that that disappeared. Because now when I try direct substitution, I do not get a bad thing. I just plug in 1 where the x is, and I get 2. Which is the same answer I had earlier when I plugged a 1 into 2x. Most of my students are liking this better for some reason. I think the algebra is a little less scary. There's no h's. But again, on your homework, let me steal your packet. On number 1, this says, here's a function. Please find the slope at 1, -4, and at 5, 0. So if you want to do method 2 on your homework, that means you're going to have to do this twice for each of the points that I gave you. Whereas if you go with method 1, you do that once, and you just plug into the little formula that you got at the end a couple times to get your final answers. It's totally up to you which formula you use. You have that discretion on your assignment. Okay, in the last couple seconds, or minutes, sorry, of class, I want to showcase one other thing for you real quick. And this might be something you just have to do somewhere you have room. I don't know if there's a scratch piece of paper somewhere in there, like one of those blank pages in the near future, but I'm going to try and come up with something kind of similar to number 1 without the actual problem. Let's say the function I give you is 3x squared minus 4x, okay? And let's say that I was forcing you, for whatever reason, to use the first method, the limit as h approached 0, of f of x plus h minus f of x over h. So I want to share with you, most of my calculus students, when they had to do this at the beginning of the school year, they would write this down. They'd write their limit, because they knew I'd get real mad at them if they forgot their limit. They'd put the over h. They'd even come up here and subtract, in parentheses, mind you. I was always very happy that they used parentheses, their function. And then they would like pause right here, because there was always some hesitation about what they needed to do where the f of x plus h was. But they had no hesitation at all about what their function was and about the h needing to be in the denominator. But this was where things were tricky for them. And don't write this, because I want to show you one more time the bad thing that they always liked to do. They would take that function exactly as it was and add an h to it. That's not our process, though. This is not taking x plus h and substituting into the function. So this has to be something that you kind of proactively make sure you're not doing. This is aligned to number 1, by the way, if you want to think about that. Okay, so in slow-mo again, my function that I made up is 3x squared minus 4x. If it were a nice Algebra 1 question, I asked you for f of 5, you would say, okay, where the x is, I need to plug in a 5. Oh, but there's another x over here, so I also need to plug in a 5. The 5 goes in everywhere the function had an x. And then you do the math. I'm asking you a very similar thing, but it's just not a 5, it's an x plus h. So that means where the 5s were, I need to evaluate this function at x plus h. Both times. So over here, in my limit, the situation that I'm going to find myself in looks like this. And now the algebra has to happen. I think some of you are just getting yourselves convinced now that you're not going to do method 1 after seeing this, which is fine. You can do method 2. But if you want some guidance on what algebra would have to happen here, I could definitely distribute that -4. That's no big deal. I could also distribute the negative. Up here, there's a box for that, x plus h. It's x squared plus 2xh plus h squared. We just saw that one. And then I just need to distribute a 3 into my result. So if you're curious, which I know some of you are like, Blakely, quit it. I'm not curious at all. But the result of this in a cleaned up algebraic manner would be 3x squared. That's taking the x squared from my box and multiplying it by 3. Plus 6xh. That's the 2 xh's from the opposite corners, now multiplied by a 3, plus a 3h squared. Distributing here, minus a 4x minus a 4h. Distributing here, minus a 3x squared plus a 4x. All over h. And I know that looks horrendous. However, what's up? Yes, I can cancel, let's see, the 3x squared, the 4x, and if you look with a very thoughtful eye, every term that's left has an h in it. So you can factor out the h just like we did before, cancel with the 1 down low, substitute in, and be done. But I just wanted to preview one time before you left how to evaluate something like that where there's more than one x, because that happens too in your life. Okay, I appreciate your patience today. I know it's a whole lot of info for a Monday. I will see you later.